Okay, so up until now, we talked about one type of reinforcement learning, and that was policy models. And here's a recap of that. So you have this neural net that predicts which action to take to maximize return. And along with that, on policy learning, where you need that policy to generate data for training the model. What I'm going to talk about now is another paradigm, another type of approaching reinforcement learning, where your model doesn't predict which action to take, but rather what the expected return would be should you take a particular action. So in policy model up until now, you didn't actually care what that total return would be. All you cared about was which action should I take to maximize that return. Now, the alternative approach, the one that I'm going to talk about in this video, is building a model that actually predicts the return that you would get should you try any of these different action options. The reason I believe these type of model, the second type, are so valuable is because they enable off-policy learning, which means your training data doesn't have to come from your model. They don't need to be generated by your policy. They can come from anywhere. Now that you're motivated, let's see how it works. The same picture that I presented before still holds true. You have this model and you have 3 output neurons, but the predictions here is not a probability of taking the action, but rather the expected return. Meaning if you take the step up, the model predicts on average you're going to end up with this amount of return. And picking the action is pretty straightforward. You just pick the action that maps to the greatest estimated return. I could take this and reconfigure it actually and come up with maybe something like this, where the output neuron has, the output layer has only one neuron, and one of the inputs to the model is going to be the action. So you will run this model 3 times, one for up action, one for down action, and one for stay action. And each time you will get the expected return should you take that action. And now you have 3 predictions, and in the same manner that I described before, you will pick the action. To summarize, the model output is not probability of action here, but the predicted value. Now, this is a good time to pause and talk about some terminology that I've been kind of like using it, but I haven't described it or defined it yet, and that is value. You know what return is. You start from any point in time, you go all the way to the end of the game, you accumulate the rewards, and that is your return. If you start from the same state, probably you'll end up with different returns, even though you're using the same policy, because there is some probabilistic nature to this thing. Now, if you get the average of the returns, you end up with value. Value is expected return. It is the average that you would get if you played this game many times starting from this state. So what we're talking about here really is the expected values should you take a particular action. And there is a name for that. That is called Q. So you will see that quite a lot in reinforcement learning. It's called a Q model, not a value model necessarily, but Q model. And Q model, or Q for any state and action, is the value should you take action A. And this is a Q model. Next, I want to talk about this pick action box. How do you pick action such that you do both exploration and exploitation? So picking action here is going to be kind of like flipping a coin. You would say 20% of times I'm going to pick a random action, but 80% of time I will pick the action that maps to the highest Q value. When you pick the action that gives you the highest value or the highest return, that's exploitation. When you randomly pick an action, obviously that's exploration. So now I want to talk about training, and in particular I find it very fascinating that you would be able to use data coming from any sources to train your model. Now let me show you the intuition behind the training. Here's the definition of return. There's nothing new here. Return at time zero is the immediate reward plus discount factors times the subsequent rewards. Well, you could refactor it and write it as follows. Return at time zero is reward, immediate reward, plus discount factor times the return at the next state. Q or value are expected or the average return. So what you have up there, you could still hold it true if you replace return with Q, because these are averages or expected values. And what we are saying here is the expected return should you take action A0 at the state S0 or at time T0, that will be the immediate reward plus discount factor times the maximum expected reward you would get from the next time step. And the argmax stuff here, it really just means that taking the action that would give you the maximum return. And that would be really following your policy. This is a key equation. There is nothing new here, but that's where we're going to derive our loss function. Now think about it this way. Now if I go to the field and collect data, I will end up with different states, S0, S1, S2, whatever, and I will be logging all the actions that were taken, and I will also get the rewards, because the reward is not a function of your model, it's just the function of the environment. No matter what policy you're using, you take an action, the state changes, and you will get some feedback or some reward. So you will get all of this regardless of what policy you use. The states and the rewards are there. And if you have a neural net that takes the stuff in the state and the action and just outputs some Q value or some prediction of Q value, you can measure its errors as follow. Now that you have this equation up there, the error would be this minus this minus this. In other words, if I move these two terms to the left, I should end up with 0. But because the model is not perfect, there's going to be some deviation. And that is the error that you will try to minimize. The model is bootstrapping itself, is trying to better predict the values that at least matches up to the next state. And by repeatedly doing this, the model gets better and better. And by the way, this algorithm, this time step bootstrapped way of training the model is called temporal difference learning. I want to make a clarification, and that is return and as a result value and Q are all for a given policy, meaning that from the same state, if you change the policy, the return, the value, and Q will change too. So when you look at this model that we're building, it looks like we don't have a policy. We're just building a model of Q. So how does that make any sense? Particularly in light of the fact that the training data doesn't come from any particular policy. So the answer to that question, to this ambiguity, is that the policy that you're following and building this Q on is this. The policy states that we will always take action that maximizes Q value. So that's that. Now with that, I'm going to switch to the code demo for the example of the game of Pong. So this is very similar to the policy model that I demoed before, but this time it's a DQN model, and DQN here stands for Deep Q Network. We have a similar neural net that takes the image as input, run it through a bunch of convolution networks, fully connected layers. At the very end, you have 3 neurons, one per action. And what is different between this and the policy network is that the final layer, the output layer, doesn't have normalization or softmax or anything like that. In other words, this is not a classification, it's a regression. The prediction of Q values can be any value, and as a result, there is no activation, if you like, at the end. Let's look at the code. We are going to run through an iteration of 200 times in this case. And what we will do is that we will generate data and store those data in a list, if you like. And each element of the data is going to be the current state, the action that you took, the reward you received, the next state, and whether it was done or not. And remember, this is off-policy learning. So this data doesn't have to come from the model that we're building here. However, having said that, we do use the model to generate data, but for a certain percentage of our data, we just randomly select action. We don't even use our model outputs. What I'm doing next is to look at the length of this list or queue that I've been collecting as a result of running the game. And once it's beyond a threshold, once we have enough data point, we sample out of it. These data points don't have to be sequential. And now we're going to calculate the loss. So let me refresh your memory on what the loss is. The loss is essentially error squared, and error is the Q value that you get from a state minus the reward minus Q value from the next state, or the argmax of it. We're going to run our model on the states to get the Q value, and this Q is essentially this. Next, we're going to calculate this piece essentially, and that is right here. You use the next state. Now in the code, instead of S0 and S1, you have S and NS. NS stands for next state. This is what you see here, times gamma plus reward. Now this term, we call it target, and your loss is essentially the mean squared error of the Q and what the Q should be based on our bootstrapping, which is this. Next, you do backpropagation, and then you'll optimizable step. Now, there is a detail that I left out up until now. It turns out your training will be more stable if you don't pull out both values of Q at S0 and Q and at S1 from the same model. So this doesn't really have a scientific explanation, but I guess after trial and error, people have found that it's best to have two identical models. On one of them, you do the backprop and gradient descent, and once in a while, you will update the other model based on the parameters in this model. So they start identical, they do diverge a little bit, and then you keep making them identical. And that's what's happening here in the code as well. So there's the update frequency. When that happens, you essentially take the model parameters and then load them into the target model. Otherwise, they're identical.